getting a sense for the way space-time works in special relativity is very challenging, and one of the ways that traditionally we become accustomed to this and help wrap our minds around the weirdness is to challenge ourselves with paradoxes. Almost invariably, they end up having to do with simultaneity, because it's the relativity of what right now means that is really so counter to everything that we are used to seeing. So in this optional clip, I'm going to take advantage of my time and go through two of the most famous paradoxes in special relativity and discuss them in some detail, and hopefully that'll help clear things up. And I suspect spur a lot of forum discussion, because I'm not going to manage to clear everything up here. So let's start with the ladder paradox. The ladder paradox is, if you want, urban parking problem. The idea is you have a long ladder of length L and a short garage of length G, but G is less than L, and you want to fit the long ladder into the short garage. And the idea is very simple. You come running with a ladder at the garage at a very high speed. Then, therefore, the long ladder is going to be Lorentz contracted to the point, if V is high enough, where it is shorter than G. Notice that by making V close enough to C, I can make the Lorentz contracted ladder as short as I want, and voila, the ladder fits in the garage. The ladder fits in the garage, but note, it only fits in the garage while it's moving very rapidly to the right. An obvious puzzle occurs because this may be true, but relativity says I can equally well view the same situation from the point of view of somebody sitting on top of the ladder. And from the point of view of the ladder is at rest. That's an inertial frame. The ladder is moving with a constant velocity to the right, v. In the ladder frame, the ladder itself is stationary, while the garage is moving at exactly the same speed v, but to the left, approaching the ladder. But from the ladder point of view, the ladder's length is L. It's at rest. On the other hand, the garage is going to be Lorentz contracted, so the garage is going to be even narrower than it really is. So in the ladder frame, we obtain the following picture. And the two seem to be in conflict. In the picture on the left, the ladder is in the garage. In the picture on the right, there is no way the ladder could be in the garage, because the garage is even shorter than its rest length, which is, as it is, shorter than the ladder as we see at the top. You can make the puzzle sharper by saying, imagine that at the instant over here in the frame on the left, where the ladder is inside the garage, I close both doors. What happens then? Now I have a ladder in the garage, and that was unambiguous. The doors are closed. So let's resolve this issue. There is, as always, no real paradox. There's only confusion. And the confusion, as I said, is always to do with simultaneity. And I'll solve this problem twice. The first time, algebraically, using Lorentz transformation. And then I'll demonstrate graphically how the solution works, and along the way play with space-time diagrams and what we can or cannot read off of them. But I want to convince you that Lorentz transformations are useful. So to use Lorentz transformations, what we do is we have to be very careful that we're not talking about wishy-washy things. We want to be very specific about what are the things we're talking about, and the things we talk about are events, things that happened. And they happened at a particular place at a particular time. So what are the things we know? In order to use coordinates, I'm going to set up my usual space-time diagram, if you want, or my coordinates. I'm going to have the black coordinates representing the garage, because I'm thinking of the garage as at rest, and the ladder is moving to the right, and its coordinates as seen by the garage are t prime and x prime. I have to pick an origin for each of these, so I'll pick the left end of the garage. Remember, the ladder is moving to the right, so the left end of the garage is going to be the origin for coordinates on the garage. So the garage stretches from x equals 0 to x equals g. So in the garage's coordinates, the garage itself, where this is x and t, the garage will be something like this, and this will be the point x equals g. And the garage is stationary, so it just sits there. The interior is the garage. I will pick the left end of the ladder to be x prime equals 0. And so, of course, the ladder is moving to the right. So if I set things up right, and I'm going to try to do that in the standard way that I like, the world line of the left end of the garage, which is also, because it is x prime equals 0, this is going to be my t prime axis. This describes the motion, the straight world line, describes the motion of the left end of the ladder, and at some point, which I am going to call by convention, t equals 0, and also t prime equal to 0, I will call that, pick as that event number 1, or event number 0 if you want, the instant when the left end of the ladder enters the garage. So at this point, the ladder is all the way to the left of the garage. What about the right end of the ladder? Well, the right end of the ladder will be, by construction, a distance L as seen in the primed coordinates to the right of the left end of the garage, so at coordinate x prime of the right side of the garage is equal to L, and it too, of course, will be moving at speed v, at the same speed v, so its world line is going to be a parallel line here. This is the world line spiritually drawn of the right end of the garage, and as I have drawn it, you can definitely see that at t equals 0, when the left end of the garage, of the ladder, enters the garage, the right end of the ladder has not yet exited the garage, and therefore, at this point, and in fact, throughout the time that I'm going to mark out here, that this whole region is a region where the ladder is contained in the garage, and then at this time the right end emerges first and later the left end emerges. So the fact that I've drawn this to exist is the statement that while g is less than L, g is bigger than the square root of 1 minus v squared over c squared L. I have made the velocity high enough that the Lorentz contracted ladder does fit in the garage. Okay, so this is the event that I will call event number 1, and this here is event number 2. Event number 2 is the instant when the right end of the ladder is about to emerge from the garage, and that occurs, of course, at a position x2 equals g, as seen by the garage frame, and of course at that same instant, at that event, is the event where the world line of x prime equals L, which is this blue line, the motion of the right side of the garage, intersects x2 equals g. So that's event number 2, the intersection of this green line with that blue line. And I can compute it. In a moment I will. And then the question of whether the ladder is inside the garage at any point or not is the question of which event came first. If event number 1, the left end of the ladder coming into the garage, precedes event number 2, the right end of the ladder emerging from the garage, then the ladder's in the garage. And in this picture it clearly is, as seen in the frame of the garage. But the question is, if on the other hand, event number 2 precedes event number 1, that means the right end of the ladder protrudes from the garage before the left end is in, the ladder was never in the garage. So let's figure out the order of these two events, and again, we will use Lorentz transformations. So I've written out here the full set of Lorentz transformations, front and back, forwards and backwards. As you note, they differ only by flipping the sign of v. And then I'm going to ask, what is the time as seen by the garage frame at which the world line of the right side of the garage meets the world line of the right side of the ladder. Remember, this was the instant when the right side of the ladder pokes out of the right side of the garage. And so I look at this equation and I say x prime 2 is equal to L, so I set L over here, and that is going to be equal to x. X is g because it's at the right side of the garage. And then minus v times t2, and then divided by the square root 1 minus v squared over c squared. And, okay, from this I can solve. Everything here is known except for t2, so I multiply by the square root, as I'm always doing. Move the square root over to here. Notice I get the foreshortened length here, and what I find, moving things around, is that vt2 is g minus L times the square root of 1 minus v squared over c squared. By construction, we said that this is less than g, so vt2 is positive. Because I was running fast enough, this number is small enough the Lorentz contracted ladder fits into the garage, that means its right end will emerge from the garage after the left end entered. Perfect. That's what we set up in the garage's frame. The ladder fits into the garage. How does this look in the ladder's frame? Well, and indeed, there is this whole time, as I said, between the time the left end enters and the time the right end exits, that the ladder is completely contained in the garage. Good for us. On the other hand, what happens if I look at the same thing from the point of view of the ladder? What I want to know is at what time did, as measured by the ladder, did the right end of the ladder exit the garage? So I want t prime at this same event. That turns out to be easier to extract from the inverse transformations. So again, x is equal to g. So I put a g over here. Over here, x prime is equal to L. And I want t prime. So again, I can solve for t prime. And I find that vt prime, again multiplying through the square root, I find that vt prime is the square root of 1 minus v squared over c squared times g minus L. Now, g is less than L. This is a number less than 1. t2 prime is negative. Remember that t prime equals 0, and also t equals 0, was the time when the left end of the garage entered the garage. But here the right end of the garage emerged before. So indeed, in the ladder's frame of reference, the ladder was never in the garage. You couldn't close both doors because, as far as the ladder is concerned, before the tail end of the ladder entered the garage, the front end of the ladder was protruding. So what happens, you ask, if the garage owner, in his frame, when the ladder is completely, as he sees it, contained in the garage, swiftly closes both doors? Well, let's follow that in a graphic representation, which will give us a chance to play with space-time diagrams and see some of their strengths and limitations. We could also do the calculation this way, but I want to demonstrate a graphic method of solution. So hopefully, what did we get from here? We got from here that the source of the paradox is the simultaneity issue. In the garage's frame, indeed the ladder is contained in the garage. In the ladder's frame, this never happens, and the reason is that simultaneity is relative, and because the ladder is moving, the relativity of simultaneity means that at the same time that, say, the left end entered the garage, in the ladder's frame, the right end was already out. Okay, so what's our graphic representation? Well, here's our graphic representation. This is already familiar. I was here careful to remind myself that I'm plotting CT, so the red line that goes off at 45 degrees is the world line of a light beam. We don't need a light beam here, but it helps me to draw the t prime, ct prime, and x prime axes so that the light cone bisects them. And what I have here, these two black lines represent the garage. These two blue lines represent the world lines. X prime equal to 0 is the t prime axis, and x prime equals to L is the world line of the right side of the garage. And so this point here is x prime equal to L. And both sides of the garage are moving, of the ladder are moving. Both sides of the garage are stationary. I may have called the ladder garage, but hopefully you understand what I am saying by now, and you're used to my ambiguity. A word on scales in these diagrams, and a very important point. So suppose that I were to draw a grid of lines. So these are lines of constant t, these are lines of constant x in some units. So these are, and I've picked the units so they're compatible. In other words, that if in some units this is 1, 2, 3, 4, so my garage in this case is precisely 4 units long, then CT is also 1, 2, 3, 4, and you can see that because these things intersect the 45-degree light cone. And so I've drawn these. How do I draw the point t prime equals to 1? Where along the t prime axis is t prime equals to 1? And one way to think about it, one naive way is to just measure this same length along this axis, and because it is the axis is not vertical, that would lead you to some point around here. And you'd maybe try to set that as t prime equals to 1, and that would be incorrect. The point is that the distance along this axis, in general, distances in this two-dimensional plot are completely meaningless. Well, how do you measure distances? Well, the distance is between any 2 points is the square root of the difference in x squared, the horizontal difference, plus the vertical difference squared. That's the Pythagorean theorem, which applies very well to the Euclidean surface of this tablet upon which I'm drawing it, or to the Euclidean surface of the slide. But this is not a physical quantity. In particular, there is no reason why it isn't all related to x prime squared plus c squared t prime squared. It's not a physically invariant object. Lorentz transformations change it. And indeed, this distance means nothing physical, and reading it off the graph produces no useful information. So it is not true that I can measure off distances the same on the same scale as I did over there, and thusly figure out where the t prime equal to 2, say, point is. So how do I do it? Well, if I really want to plot where along the t prime axis the point, say, t prime equals to 1 is, what I need to do is the following construction. Remember, there is something that is preserved in this weird and is physically meaningful in this Lorentz relativistic world, and that is that c squared t squared minus x squared is the same as c squared, sorry for the color violation here, minus x prime squared. And along the t prime axis, well, that's the point where x prime equal to 0, so I can erase that. Furthermore, along the t prime axis, x is equal to vt, because this describes the motion of the left side of the ladder, which is moving with speed v. So I get that c squared minus v squared t squared is equal to c squared t prime squared. I am going to eventually figure out exactly the time dilation, relativistic time dilation formula, which is that t prime is t times the square root of 1 minus v squared over c squared. What does that mean? That means that the time here, t prime at this point, is less than 1. If I draw the point t prime equal to 1, it will be somewhere over here. And the point t prime equal to 2 is somewhere over there. Notice that the scales of the two axes are different. This is confusing and troubling. It has to do with the fact that what is physically meaningful is this Lorentzian distance, if you want, this sort of weird distance with a minus sign, rather than the Euclidean distance that is the distance that we observe in the graph. And you can perform with negative value for the interval a similar calculation, and you will find that the scale of the x-axis also is extended. And in general, in any space-time diagram, the scale is smallest in the observer's for the observer that is at rest. In other words, if I draw here the lines of constant x, constant t prime, and the lines of constant x prime, then I find indeed that if I drew x equals 1, 2, 3, and ct is 1, 2, 3, and I then want to draw the lines of x prime equal 1, 2, 3, then I need to draw them approximately here, and then x prime equals 3 would lie way over there, and likewise t prime equals to 1 would be way up here, and 2 and 3, and so on. So the scales in this diagram are misleading. If you really want to lay scales on it, you need to use the invariant interval or the appropriate hyperbolas to draw these distances. This is one of the reasons why doing calculations from these graphs can be confusing. The thing that is always meaningful in these graphs is the order of things. In other words, what is true is that the entire region above the x-axis is positive t, and that an event that is farther up than another is later as viewed by this observer, and similarly, the entire region above, in this sense, the x prime axis, is at positive t prime, and the region below it in this direction is at negative t prime, and the order of events can be read off from this grid. So you draw the grid, and if you have some random event over here, the infamous birthday party that we spoke of over here, then to read off its x and t, we draw parallel to the x and t axes, and we see that this happened at x a little larger than 2 and t getting close to 4. If we want to plot this in x prime t prime coordinates, we draw lines parallel to the axes, because remember, this line is a line of constant t prime. It's parallel to the x prime axis, and this is a line of constant x prime, and we see that this happened at x prime a little less than 1, and t prime somewhere between 2 and 3 is when this birthday party happened. So this is how we read coordinates off of these space-time diagrams. I hope that was helpful. And now I'm going to erase all these grids, which are just confusing, and note that I have marked here our favorite two events. Event number 1 is the instant t equals 0 when the left end of the ladder enters the garage. And notice that, as anticipated, because I made this point, which we know is L root 1 minus v squared over c squared, less than g, then the entire garage ladder at this point is enclosed in the garage. And this goes on until the time of this event labeled 2. Event number 2 is the instant where the right end of the ladder starts protruding from the garage. And so, as I suggested there's this whole region here from T1 to T2 where the entire ladder is inside the garage. Okay, so now we can ask, what happens if I close the door? Well, if I close the right door, and I forgot to note, on the other hand, we can see directly from this diagram that at event number 2, while in the garage frame, event number 2 happened after event number 1, and indeed, for this whole time, the ladder was inside the garage. In the ladder frame, event number 2 occurs before event number 1. Remember, these are all the events that are simultaneous with the ladder entering the garage. Event number 2 corresponds to some negative value of t prime down here, and indeed it preceded, as seen by the ladder, event number 1 is seen by the ladder, the right end poked out of the garage before the left end got in, and the ladder was never in the garage. So now you can ask, all right, well, what happens if I close the door? Well, if I close the door, then let me decide that the front door of the garage, the door of the garage at G is going to be closed. What that means is that the right end of the ladder travels. At event number 2, it hits the garage door, and from that moment on, the right end of the ladder is at rest and moves along this green trajectory. Now, the way we're used to thinking about it is a ladder is a ladder. If at this point in time the ladder stopped, then the entire ladder stopped, and voila, we have the entire ladder contained in the garage as seen by the garage frame. But this is confusing because in the ladder frame, remember, when this event happened, in the ladder frame, the left end of the garage wasn't in the garage yet. The left end of the ladder wasn't in the garage yet. So what is this saying? Well, the answer to this is that we have made an unwarranted assumption here, which is that when you stop the front end of the garage, of the ladder, you also stop the left end of the ladder. Remember that at this point, the right end of the ladder smashes into a wall and it stops. Now, what is going to happen is that the back end of the ladder, just like our slinky when I dropped it, has not yet heard that the front end of the ladder has crashed into something. The left end of the ladder continues to come at speed v until somebody tells it. What tells it? Well, a sound wave, of course, will be propagating down this ladder as the front end of it crumples, propagating back to tell the back end of the ladder, wait, there's an extra force, we need to stop. How fast does this sound wave travel? Well, that depends what the ladder is made of, but I know a limit. The sound wave will not travel back to the ladder in its own frame or in any other frame that's happily an invariant faster than the speed of light. So at this event, when the front end of the ladder crashes into the door, you can imagine a sound wave propagating back up the ladder to the left, trying to tell the left end to stop. So how fast can the signal propagate? Well, this is the fastest it can propagate. The fastest that the rear end of the ladder can hear that the front is stopped is the speed of light. So I've drawn a light speed 45-degree propagation of the signal from the back of the ladder, from the front of the ladder to the back, telling it to stop. And if this were the case, you notice that by the time this light beam reaches the back end of the ladder is well within the garage, because even in the ladder frame, we are now talking about a positive time, right? And so time has, remember, the left end of the ladder entered the garage here. By now, the left end of the ladder is well in the garage. If you stop the front end of the ladder, the back end would keep coming. You would not be able to stop it until it was in the garage. Now, what happens at the moment to the actual ladder when the sound wave propagates and reaches the back? Well, the energies involved are such that most ladders would probably blow themselves up to smithereens or crumple to atoms. But in any event, by the time the rear end of the ladder hears that the front end has stopped, and maybe we have a very powerful ladder and it's elastic and it springs back out and re-expands, by the time all that, and crashes into the garage door, but by the time all of that, any of that happens, the ladder is well within the garage. And so the fact that you managed to close the doors is not an interruption. When you close the doors, at this event, the ladder the left end of the ladder was already in the garage. This door stopped the front end, but the left end kept, as seen by the ladder, the left end kept coming. So there is no contradiction. There's a lot of kinetic energy to be lost, and there might be a great explosion. And of course, if the ladder doesn't blow itself to smithereens, then of course there will be an elastic rebound. The back end of the ladder will now pop back to the right at high speed. High speed, but less than the speed of light, crash into the garage door, and then whatever happens will happen. But you can indeed enclose the ladder in the garage, at least in the instant. And the error that we were making when we were trying to compare the two frames and say you stopped the ladder at the front was the assumption that the ladder is a rigid object. One of the things we learn here is that objects with a given shape and size do not make relativistic sense. An object, this pen, has a size and the shape in the sense that when I move this side of it and I drop it, the other side moves as well. This could not relativistically be true. In fact, if you look very closely, it's not true. When I move this side, actually the pen bends a little. A sound wave goes traveling down the pen, and if it were a slinky with a slower sound wave, we would be able to see it. And when the sound wave reaches here, then and only then does the other end start rising. When you're dealing in relativistic speeds, this little time delay makes all the difference. So thinking of an object as having a given size in relativistic terms is a really bad idea. So hopefully we've learned some results of some of the ways to think about relativistic kinematics, and hopefully you understand the resolution of the ladder diagram, though, as I said, it takes seeing the solution and then thinking about it a lot and arguing, and I hope the forums will be lively. A perhaps even more famous paradox of special relativity is the twin paradox, and the twin paradox I'm going to demonstrate graphically. We won't do too many calculations. There's not much to compute. So what's the story with the twin paradox? We have two twin brothers or sisters, and they live until some age on Earth, and then at some point, one of them gets into a spaceship, traveling at high speed in some direction, close to relativistic speed or traveling for a long time, and for a long time this twin travels off into space, so he's moving to the right. And then after having achieved a certain distance, he hops on another spaceship, moving at the same speed but in the opposite direction, and after a while returns to Earth and gets reunited with his twin. Now, of course, when they left, they were the same age. So the question is, when twin number 2 returns from his voyage, who's younger? Are they the same age? And the answer is no, they are not the same age. And it's easy to make that calculation, but then it's puzzling to understand, wait a minute. So let's first start with the question, who's younger? Well, we have here the usual two events, event number 0 and event number 1. And the coordinates of these events, again, I have my usual axes, x prime, t prime. T double prime here is a new time axis, which is the world line of the twin number 2 on his return. But I'm going to start by dealing with this segment. It is sort of clear by symmetry that everything that happens along this segment happens symmetrically along this segment. And so let's figure out what happened at event number 1. So let's say that the twin on Earth measured a time t1, and therefore the twin that was traveling measured a time t prime 1. Now, where did this event occur? Well, this event occurred at a position x1, which is equal to vt1, because the twin was moving with speed v. But it also occurred at position x prime 1, and we know what x prime 1 is. X prime 1 is 0, because in his own frame, the moving twin was at rest, and therefore we can now the point is that we can now compute the invariant interval between here and here in the two different frames and set it to be the same. So that tells us, and again, I'm not going to maintain all of the colors, that c squared t1 squared minus x1 squared has to be equal to c squared t1 prime squared minus x1 prime squared. But we know some things. We know x1 prime is 0. We know that x1 is vt1, so c squared t1 squared minus v squared t1 squared is c squared t1 prime squared. And we do the usual calculation, and we find that t1 prime is t1 times the square root of 1 minus v squared over c squared. Or written otherwise, t1 is t1 prime divided by the square root of 1 minus v squared over c squared. So that what we are saying is that this event appears to the stationary twin to have happened at a later time than it appears to the moving twin. Why do I know it's a later time? Because I'm dividing by a number smaller than 1. Well, yeah, you say, of course. But on the other hand, I can draw this line and say that is true, but that's because I am measuring the time at event 1. I can invent an event number 2 here, which is simultaneous with the moving twin's decision to return, and that event number 2 clearly occurs at a time earlier than t1, and if I compute, I will find that in fact t2 is exactly t1 prime times, you can compute this. It's, again, these two happened at the same value of t prime, but one happened at x equals 0, and one happened at x prime equals 0. And the symmetry between these is, of course, the usual understanding that we have. The stationary twin sees time dilation, sees the moving twin's clocks running slow, and the moving twin sees the stationary twin's clocks running slow. So the twin whose coordinates are black thinks that his brother is aging slowly. The twin whose coordinates are blue thinks his brother is aging slowly. So how is it that but on the other hand, it is clear that since from at this point t1 is clearly more than t1 prime, and since this is t1 prime is how much the moving twin aged, t1 is how much the stationary twin aged, since the same thing is now repeated on their return, it's clear that if this is true, then 2t1 is equal to 2t1 prime divided by that, and upon the return, the stationary twin will be older. How can that be? We just computed that on the one hand, I thought we had this symmetry relation. Relativity tells us that if the black twin sees the blue clock running slow, so does the blue twin see the black clock running slow. What ruins relativity here? Well, when you think about it, it's pretty clear that these two twins are not related by Lorentz transformation. They were related by Lorentz transformation as long as twin number 2 was moving to the right at this constant speed v. But there is a big difference in their life histories, and the big difference occurs, of course, here. At this instant, twin number 2 jumped from one spaceship to the other. He was not inertial. At that instant, twin number 2 was actually accelerating. Not only that, but as I drew it, since his velocity changed instantaneously, the rate of change of his velocity was infinite, he was experiencing an infinite acceleration. So that's not very realistic, but it makes the calculation simple. But this is why the life history of the two twins is different. It's different, and it's not, you don't expect symmetry. If blue thinks black clock runs slow, then black thinks blue clock runs slow. The difference is that one of them accelerated. And the one who accelerated will be younger, and this is brought out by drawing some auxiliary world lines here. So what I've done is, at this event number 1, I drew before the t double prime axis the world line of the moving twin as he returns. I can now draw the auxiliary light cone and therefore the x double prime axis. And here we see the resolution to the mystery, because remember before I suggested that we introduce event number 2 over here, which is, what is this? This event is from the point of view of the blue twin, of the moving twin, as long as he is moving away from Earth. Event number 2 is simultaneous with event number 1. So if these guys were exchanging messages, then indeed, when he decided to change, to jump ships, the moving twin would have been convinced that his brother was younger than he was, and just as the stationary twin would have been convinced that his brother was younger than he was. Until that point, everybody's inertial and life is symmetric. But at the moment that he jumps ships, what happens is that now, what he considers, when he's moving to the left, to be simultaneous with this same event number 1 is actually event number 3 over here. His line of simultaneity changed because he changed velocities instantaneously. So, in particular, over the instantaneous jump from ship to ship, his brother aged this much. All of this aging took place essentially instantaneously during the instant that the moving twin jumped ships. This is the resolution. This is where the symmetry is broken. Indeed, this segment is less the time that the twin on Earth aged during this segment is indeed less than the time that the moving twin aged here, and the same by symmetry is true up there. But when you add this extra segment from jumping ships, it's unambiguous the twin on Earth is older. This is not a contradiction to relativity. There is a difference between them. You could measure the difference. One of them accelerated. Okay, so we've cleared up the paradox. We understand that the twin that accelerated remained younger, and there's not a violation of relativity because you could measure the difference between the two. One was inertial, one accelerated. Okay, but there's an unsatisfactory feeling to this resolution because what I've essentially done is hidden all my ignorance in this instant of infinite acceleration, where instantaneously, as seen by the moving twin, his Sid suddenly aged all the difference that makes up for the Lorentz time dilation that he otherwise would have seen. This infinity doesn't make sense. Can I do better? Well, of course I can do better. What I really want to do, and in fact the only physical thing to do, is you can't have infinite acceleration. You could apply a finite acceleration. You could round off this corner a little bit. And now I have a story without infinite acceleration, and you can ask, well, what happens here? Well, computing here is a little bit more difficult because now the moving twin is not in an inertial frame. the way I cheated before was that I jumped from one inertial frame to another inertial frame, and I ignored the acceleration that this implies. Now I have to deal with this acceleration, and that requires a little more calculation than we have, but we can get a sense for what this implies by imagining here's a trick that will cause him to accelerate. Remember, I want him to be moving to the right and then accelerated to the left. And the way I'm going to do this is I'm going to imagine that somewhere out here, I don't know, a little distance, not exactly in the direction that he's moving, so he doesn't crash into it, but not far from there lies a star, a heavy, massive object. And what I'm going to imagine is that as this twin approaches the star, he's accelerated and then goes into a hyperbolic orbit and is deflected by the star so that he comes back to Earth. So basically, I arrange the angles so that he overshoots the star, gets captured, affected by its gravity, loops around it, and comes back. Okay, now, since he was going very fast, I wanted this to be relativistic, he needs quite a bit of acceleration to flip the direction of that velocity, so he'll have to get near the star, or the star has to be very massive, whichever way you want to think about it. And this gives us another point of view on what is going on here and why it is that in an unambiguous way, not the usual time dilation that is symmetric between two inertial frames, but in an asymmetric way, honestly, physically, the moving twins clock was running slower than the stationary twins clock, and it somehow has to do with the acceleration. And the idea is, imagine breaking up the trajectory into sort of three pieces. Piece number one is the piece over here until he approaches the star. So at this point, we imagine we can ignore the gravity of the star and everything is inertial, and indeed, the stationary twin thinks his brother's aging slower, the moving twin thinks the stationary twin's aging slower, and indeed the same thing obtains here, and all the symmetric Lorentz invariant, Lorentz transformations back and forth describe what was going on here. And then there's the region in between these two events where there's this high acceleration, and now we have a sense for what is going on here. We know that during this period, the blue clock runs slower than the black clock, but from our point of view, it's somewhat clear. The black clock is very far away from the star. The blue clock is running very near to the star. The blue clock runs slow during this period because of a gravitational redshift. And how much gravitational redshift? Well, that depends how massive the star is and how close. And that is determined by how massive the star has to be and how close you have to get to it in order to deflect this velocity v, or change your velocity from plus v to minus v, zooming you back towards Earth. So at least without a calculation, you can do a calculation. But at some intuitive level, it is clear that indeed the accelerating phase of this moving twins trajectory is the phase of the journey during which unambiguously the moving twin ages less than the stationary twin, in a way on which they would both agree this is not a question of whose clock is measuring it, but he literally is aging slower. This is because we can now see the asymmetry. He is at the bottom of a gravitational well and his brother at the top. So thinking about gravitational time dilation is a very powerful tool, and in particular it gives us a way of reasoning our way through the twin paradox and understanding what might be going on.